Now we consider what we can learn by using both the concept of a stream function and a flow potential together at the same time. Let's start with the simplest case. Let's consider ideal, incompressible, and irrotational flow. So ideal, this means that there's no viscosity. Incompressible, divergence of our velocity is equal to 0. Irrotational, the vorticity, which is the curl of our velocity, is 0. So the curl is 0, the divergence is 0, and there's no viscosity. All right. So we know that for satisfying these latter two, u is equal to the curl of the stream function that satisfies that the divergence of u is 0 by construction, and it's equal to minus the gradient of phi that satisfies that the curl of u is equal to 0 by construction. The curl of psi is therefore also anti-parallel to the gradients of the vector potential phi. And from that, and from looking at the components, you can see that we actually have the relationship of the two. That if you took the gradient of psi, and here I'm going to treat psi as a scalar for like a 2D flow. For 2D flow, psi is just the z component. This is not strictly necessary, but as you go to higher dimensionality, what I'm about to show you, you have to use a little more care. But for 2D, you've got some very nice simple relationships. The gradient of psi dotted with the gradient of the vector potential phi, this is equal to 0. Well, that's interesting. What does that tell us? It tells us that phi and psi, right? Psi and phi, these are orthogonal functions. Right? Their gradients don't point in the same direction. There's no projection of the gradient of psi onto the gradients of phi. There's no dot product between the two of them. So they're orthogonal functions. And there's a whole bunch of power that comes out of this. And in particular, this leads us to the Cauchy-Riemann conditions, which we've mentioned previously, but we'll come back to again right now for the moment. So this gives us the Cauchy-Riemann conditions. And those are that d phi dx, that's our gradient of phi, is given by d psi dy, whereas d phi dy is equal to minus d psi dx. And we also know that if you take if you take these tell you that there exists a complex function, some function of complex variable z, which is itself equal to phi plus I times psi, where phi makes up the real part and psi makes up the imaginary part. And there's a related complex velocity w, which you can obtain by taking df dz, which gives you basically the potential bit coming from the first part and the the stream function bit coming from the second part. The W is a complex velocity, and the components of this complex velocity are u minus I times v. U here, this is the x component of u vector. V, this is the y component of u vector. And this complex velocity, there will be times where this complex velocity is a very powerful tool for solving flow, especially around objects like cylinders. It can be a very compact way of representing your overall flow. What else can we tell from this combination of a stream function and a potential? Well, we assumed that we had ideal, incompressible, and irrotational. What if we relax that? What if we're more general? If we relax in particular the requirement of both incompressibility and irrotationality, we can represent our velocity u as a combination of both the curl portion as well as the potential portion. And now we have a flow that could have both vorticity and compressibility. And here we have a bit that's compressible, but irrotational. And we have a bit here that's incompressible, but has vorticity, but is vortical. And here we've sort of decomposed our flow into these two components, these two projections. And this can be very powerful for picking apart which parts of a flow are acting in an acoustic-like way, in a compressible or sound-like way, and which parts of the flow are acting in a incompressible, vortical sort of fashion.